So an example problem here will deal with strain information given to you on the foot or again at some location on a large piece of machinery. So we'll look down here near the support. We have a rosette that's present. You're told information about that rosette right there. It just turns out to be a 45-degree rosette. But again, notice the orientation of the x-axis right there. And what we're interested in doing is taking that strain information and ultimately calculating principal stresses and angles. And so that way you could end up dealing with yield criteria. But we're just going to get those principal stresses, and we'll actually also draw the rotated stress blocks. So to start out, we're going to need to take and process. There's our strain gauge information. Right? We've got something that is shortening. Right? B and C are elongating. They're positive. And so we're just going to use the strain gauge equation 3 times. We'll end up with 3 equations, 3 unknowns. So we'll go through the setup and the solution of this. So very important, notice from the x-axis is where all the thetas are measured from. So for gauge A, we would be sitting down at a negative 15 degrees. Gauge B would be plus 30. Gauge C would be up there at plus 75. Right, from the x-axis would be 75 degrees. So all we're going to do is use the strain gauge equation 3 times. And here's our strain gauge equation right off the equation sheet. So I've just used A here. I'm going to relate it back to x, y coordinates. And so I just need to plug this in 3 times. So there would be epsilon in gauge A. And I'm going to use cosine squared of minus 15. Sine squared, and then there's the cross sine and cosine. So it's going to do that for 3 combinations for epsilon b and theta b, epsilon c and theta c. So you'll want to make sure you can do that. We're going to end up then with an expression that is solvable for the initial strains. So that'll end up being what we want to solve for. We'll use those initial strains to then go ahead and solve for principal strains. So it might take a little bit of time. You'll want to use your calculator to go ahead and solve for that. You'll invert the coefficient matrix, and you'd end up with, on the other side, an answer for your initial state of strain. So we're going to be able to find principal strains from these and then relate the principal strains to the principal stresses. So let's go ahead and take a look at what the strain state looks like. So we use the coordinate system. I'm going to draw a strain block, and I've got on the x face positive 65, on the y face positive 150, and I've got a shear strain which is going to be on the x face in the positive y direction. So I'm going to go ahead and draw that arrow right there. If I can draw 1, I can draw all 4, and I label it 1185. So I just need my initial strain state, and I can jump on Morse circle for strain. So let's go ahead and look just down here. There's going to be, right, here's our canvas. There's epsilon. There's gamma over 2. So as we work through our strain state, we're going to take the normal strain, and then here would be gamma over 2. And this gamma over 2 has to obey Morse circle sign convention. So that strain right there would be causing counterclockwise rotation, which is negative on Morse circle. So I'm going to take 1185, divide by 2. And do the same thing on the y face, right, with my coordinates. So plus 150 and then plus 593, right? That shear strain would cause the element to rotate clockwise, which is positive. So I'm going to use gamma over 2. So I'm just going to go ahead and plot those from that. Right? We should be able to quickly find the center. Right? The center is just going to be the average normal strain. So take those two, 65, 150, add, divide by 2. There's epsilon average. I also need the radius of the circle because I'm going to spin it to find my principal strains. So the radius of that circle, I'm going to highlight that triangle right here. We'll also use the pink theta here in a little bit when we actually solve for some angles. So my horizontal length is going to be 42.5. And I take 65, subtract 107.5, or vice versa. Either way, I'm going to end up squaring that value. It's 42.5 squared. Vertical distance is 593 squared. Add them all together, I get an R equal to 594. For bookkeeping later, this will be the pink theta, so we'll use an inverse tangent. We'll run an inverse tangent with the two sides there. We'll end up with 4.1 degrees. So that'll just be for safekeeping for later. Maximum strain in plane. We go back up to Mohr circle. So if we spin it, we would end up with a circle that looks like that. And so we would have an epsilon max and epsilon min. All right, we're going to hold off on calling them 1, 2, or 3 because we're still going to need the strain in the z direction, the out of plane strain. So I can use, though, middle of the circle, the center plus r, center minus r. Those will give me 2 of those. Now, this is a plane stress problem. So we derived this earlier on a problem, and it can be, again, derived from the equation sheet. So you go back to that previous example. We're going to use 3D Hooke's law. We're going to use the equation for sigma zz, set it equal to 0. So it takes a little bit of math, but you can create the relationship that says the strain in the z direction is going to be the negative Poisson 1 minus Poisson's ratio. And then you're going to multiply that by the sum of the normal strains. So we could also use principles because we know the strain invariant has to hold. So the normal strains have to be constant at any angle. So you could use either one of those to do this. And we would calculate that epsilon zz is actually equal to minus 87 microns. So with that calculation, we would now have all 3 of our principal strains. And now we can order them. So this would be, right, an in-plane strain. Right, this would be the other in-plane strain. There's our out-of-plane strain, which would fit right in the middle, again, numerically. So there's epsilon 1, 2, and 3. And so where this is powerful is we can use these principal strains to calculate principal stresses. So you can use either formulation on your equation sheet. Here it is in the strain to stress relationship. And so we're just going to end up inverting this. So we use, again, AX equals B, and that's how it would look as we set it up. So here's our principal strains. Those would be the principal stresses, right? Again, noticing the subscripts 1, 2, and 3. Here's our coefficient matrix over here. And so we end up just inverting it and solving for the principal stresses. And so that's good that we ended up solving for one of the principal stresses equal to 0. Right? We know that one of them would have to be 0 because this was a plane stress problem, being it that we were looking at the exterior or a free surface of a machine component. So from that we can calculate, well, really anything. We've got average normal stress. There's going to be tau max, right, our maximum shear stress. So we'll end up using these values when we, right, draw the rotated stress states at theta P or theta S. Actually, these would all be for a theta S maximum and average, which shows up on all the faces. So we'll go back and do our theta game. So here's our Mohr circle for strain again. Right, we had the pink theta, which we already calculated as 4.1 degrees. So 2 theta P would be the strike of the X point all the way over to epsilon max. So that strike would be made up of the pink theta plus 90 degrees more. So I'll just kind of go right back in there, a little tighter. Right, there's the pink theta, and there would be 90 degrees more. So that would give us the whole strike, 2 theta p. Solving for theta p, that answer would be in the counterclockwise direction. Theta s, take the x point, put it vertical, x prime. So it's actually very close. It's going to be a very small answer, again in the counterclockwise direction. So 2 theta s would be equal to the pink theta. So there would be our answer for theta s. So let's just kind of look here. If we rotate our element at 47 degrees, which is theta p, we'd end up with 125, right? Sigma 1. There would be sigma 3, right, on the y prime direction. So there would be the principal state of stress. Rotating it at roughly 2 degrees clockwise, we end up with maximum shear stress. So we'd have our normal, right, our average stress on all faces, and then your maximum shear stress, which would show up on the faces.